Hello, Dr. Zavadny. Here's my presentation on the mathematical analysis of COVID-19 models and projections in Ontario. Before I start, I'd like to show how logarithmic functions are used in the real-world scenarios like COVID. Earthquakes are typically measured between 2 and 10 on the Richter scale. If you took the time to examine this example, you would see how scientists take the log of the amplitude of the greatest earthquake wave to get a measurement on the scale. Now I can show how logarithmic functions can model COVID rates that we have seen in the past. In this graph, X values are determined by days after the start of the growth of cases in Ontario, February 20th in this presentation. Looking at the interval of 2558, we can see a transformed version of what looks to be a logarithmic function. As cases start to grow, the idea of flattening the curve became prevalent in Ontario. I used a graph of log x plus 1 to display how the curve of a logarithmic function exponentially decreases, the same way the curve was flattened by stay-at-home orders in the province of Ontario. Transformations applied to this logarithmic graph include a horizontal phase shift to the beginning of the interval and a vertical stretch as it lifts well above the y values of the parent graph of log x more rapidly. The only possible way asymptotes include a vertical one at 25 days in, because you can't go back in time. Another asymptote is that the population of Ontario, because vaccines are yet to be distributed, and the sky was the limit for this virus. This slide simply displays the exponential graph based off the parent exponential function of f of x equals 2 to the power of x. However, transformations cause it to be f of x equals 2.7171 times 1.028 to the power of x. It shows what happened on the interval of 134-262 when stay-at-home orders were lifted and students returned to the classes. The graph ultimately reflects vertically after that peak when lockdowns are instated. Projections as of this month display all of optimistic, pessimistic, and neutral ways in which the virus may continue. The optimistic projection suggests a transformation of f of x equals 2 to the power of x, in which the graph is reflected vertically, so negative 2 to the power of x. This means cases will rapidly decrease and slowly decrease less as the cases approach y equals 0. The only true asymptotes appearing vertically as time travel is still impossible. The pessimistic graph suggests an exponential function with a positive slope rather than a negative. The neutral suggests a similar graph to the optimistic, but with less of an instant decrease or rather horizontal compression. The two models on the left display projections at different growth rates released back in November. They both suggest exponential functions related to that of f of x equals 2 to the power of x. However, at a 5% growth rate, there is a horizontal compression causing faster increase in cases. Asymptotes continue to change and lower on the y values based on the amount of people being vaccinated. On the right, you can see a January projection on how COVID might have went with an instant lockdowns in Ontario. They resemble a logarithmic graph reflected vertically, so having a negative slope. These graphs suggest rapid decrease in cases, but less decreasing as the function approaches y equals 0. There is an asymptote there in the logarithmic function, and I agree with this as I believe it is unforeseeable as to when Ontario will be truly COVID-free. This Desmos image shows the 3% growth in red, the gradual exponential increase in cases, the 5% rate in blue, exponential increase with horizontal compression, and the negative sloped logarithmic function. Thank you so much for listening.